Welcome back to AI Research Weekly. I'm Nova, your guide to the cutting edge, always looking for that so what in the latest breakthroughs.
And I'm Onyx, here to provide the broader context and analytical depth to this week's most impactful AI developments. We've had another absolutely packed week, with over 350 papers crossing our desks just yesterday.
Yeah, it's a whirlwind out there. And the big picture this week really seems to be about agents, particularly self-evolving and meta-learning agents. It feels like we're pushing hard into systems that can not just operate autonomously, but actually design other agents.
Absolutely, Nova. That's a critical evolution. Moving beyond single-task agents to ones that can strategize their own tool creation and adapt in long-horizon complex environments. It's a significant leap in capability. And linked to that, we're seeing a strong focus on improving multimodal large language models, especially in spatial and visual reasoning. The field is really grappling with how to make MLLMs truly see and understand the physical world.
Right. And that struggle with seeing leads directly into some interesting new evaluation concepts, like cross-framing inconsistency for VLMs and new benchmarks to diagnose agent failures in tool use and memory. It's not enough to build them. We need better ways to break them and understand why.
Precisely. That need for robust evaluation underpins several of the high-impact papers this week. But let's dive into some specifics. The first one that really caught my eye, and it ties into your point about MLLM spatial understanding, is Generation Models No Space, unleashing implicit 3D priors for scene understanding.
Vega 3D. This one's fascinating because it tackles MLLM's spatial blindness not by adding explicit 3D data, which is often scarce and hard to get, but by repurposing something we already have, pre-trained video diffusion models. That's clever.
It's more than clever, Nova. It's fundamentally innovative in its approach to addressing a pervasive MLLM limitation. Existing methods often rely on explicit 3D modalities or complex geometric scaffolding, which quickly hits data scarcity and generalization walls. Vega 3D proposes that video generation models implicitly learn robust 3D structural priors and physical laws. They synthesize temporally coherent videos, so why not leverage that inherent understanding?
So they take a pre-trained video diffusion model, like a WAN 2.1 or VMEM, and essentially treat it as a latent world simulator. They're not just taking the final pixels, they're extracting spatiotemporal features from the intermediate noise levels. And then they integrate these with semantic representations using a token-level adaptive gated fusion mechanism. What's the key here with the intermediate noise levels? Is it about richer, less abstract representations?
Exactly. The paper highlights that the most informative spatial cues for downstream tasks actually emerge from these intermediate representations and the mid-denoising time steps, rather than the final, fully rendered pixel outputs. Think of it as accessing the model's understanding of the scene's geometry before it fully commits to a specific visual realization. This provides richer, more robust 3D priors that act as spatial anchors for the MLLMs.
That's a significant insight. Instead of fighting with sparse 3D data, they're distilling spatial intelligence directly from temporal consistency. And the results?
The results are compelling. Vega 3D achieves superior performance across 3D scene understanding, spatial reasoning, and embodied manipulation benchmarks. They outperform state-of-the-art baselines, and crucially, demonstrate that these generative priors offer a scalable foundation for physical world understanding. The fusion consistently yields performance gains, and they observed a strong correlation between multi-view correspondence scores of their generative models and downstream 3D understanding. For instance, WAN 2.1 T2V showed high correspondence across shifting camera views.
That scalability point is huge. It means that as video generation models get better, so too does our ability to imbue MLLMs with stronger 3D spatial reasoning without needing new training paradigms or complex geometric annotations. That essentially democratizes advanced spatial understanding for MLLMs. My only pushback would be, how universally applicable are these implicit priors? Are there specific types of scenes or objects where a video diffusion model's internal representation might still fall short compared to explicit 3D data?
That's a fair question. While the paper demonstrates broad applicability, it's reasonable to hypothesize that extremely fine-grained metrical reasoning or highly specific topological constraints might still benefit from dedicated, explicit 3D input. However, for many common-sense physical interactions and scene understanding, this approach seems to strike an excellent balance between data efficiency and capability. The plug-and-play nature also allows for future fusion with explicit signals if needed, but it really reduces the initial burden.
Okay, moving from MLM perception to agentic capabilities, another paper that really jumped out was MetaClaw, Just Talk, an agent that meta-learns and evolves in the wild. This one screams agents designing agents, which you mentioned earlier, Onyx.
Yes, Nova, MetaClaw is a poster child for the accelerating trend in agentic AI. It's a continual meta-learning framework that jointly evolves a base LLM policy and an entire library of reusable behavioral skills for LLM agents. This isn't just about an agent completing a task, it's about an agent improving its own operational architecture.
So how does it actually evolve these skills? That's the core question, right? Is it RLHF? Is it something else?
It's a combination, but with a clever twist. A key component is skill-driven fast adaptation, where an LLM evolver synthesizes new skills directly from failure trajectories. When an agent fails, it doesn't just learn to avoid that specific failure, it develops a new, reusable skill. This leads to immediate improvement with zero downtime, and they show accuracy improvements of up to 32% relative.
That zero downtime is critical for real-world deployment. You don't want your agent to stop working while it retrains. So it's learning from its mistakes and then packaging that learning into something modular?
Precisely. And in parallel, MetaClaw uses opportunistic policy optimization. During user inactive periods, it performs gradient-based updates via Cloud LoRa fine-tuning and reinforcement learning with a process reward model, or RLPRM. So you have this dual mechanism, immediate skill synthesis from failures for quick fixes, and then a more deliberate background policy refinement through RL and PEF techniques.
That sounds quite robust. What were the actual performance gains?
The full MetaClaw pipeline advanced Kimi K2.5 accuracy from 21.4% to 40.6% on MetaClaw Bench and Auto Research Claw. That's almost doubling the accuracy on complex benchmarks, and it increased composite robustness by 18.3%. They also employ a versioning mechanism to prevent data contamination and use a proxy-based architecture for scaling production-size LLMs without requiring local GPUs, which is a major practical consideration.
The idea of an agent evolving its own skill set based on real-world failures is incredibly powerful. My question is, how do they ensure that the synthesized skills are actually optimal or even safe? Is there a verification layer, or is it purely trial and error with RLPRM guidance?
That's a critical point. While the paper emphasizes RLPRM for reward modeling and opportunistic policy optimization, it doesn't explicitly detail a formal verification step for synthesized skills beyond their observed performance in evaluation. The robustness increase suggests some level of implicit safety or quality control from the feedback loop, but a dedicated formal verification mechanism for newly generated skills could be a valuable future direction to ensure broader applicability in high-stakes environments. It's an area where the agentic AI field is generally putting more emphasis, as we saw with MiroThinker H1's focus on verification.
Speaking of verification, that leads us nicely to MiroThinker 1.7 and H1 towards heavy-duty research agents via verification. If MetaClaw is about agents learning new skills, MiroThinker is about agents getting it right through rigorous checks.
Indeed. MiroThinker H1 is designed for deep research tasks, pushing agents towards more complex, multi-step problem-solving. Its core contribution is the integration of both local and global verification into its reasoning process. This is crucial because it allows the agent to not just refine intermediate decisions, but also audit its overall reasoning trajectories. It's about building trust and reliability.
So, local verification for individual steps and global verification for the whole chain of thought. Can you elaborate on how that works in practice?
The paper implies that local verification might involve, for instance, checking the output of a specific tool use against known constraints or requerying parts of the knowledge base. Global verification, on the other hand, would involve assessing the coherence and correctness of the entire research plan and its conclusions, perhaps by cross-referencing multiple sources or employing meta-reasoning about the logical flow. This is a significant improvement over agents that just try again without understanding why they failed.
And what kind of tasks are we talking about for deep research?
They tested it across open web research, scientific reasoning, and financial analysis benchmarks, achieving state-of-the-art performance. The MiroThinker 1.7 Foundation, which MiroThinker H1 builds upon, specifically improved interaction reliability through an agentic mid-training stage that focuses on structured planning, contextual reasoning, and tool interaction. So it's about grounding the agent's actions in a more reliable framework from the outset.
That structured planning and verification approach feels like a necessary step for complex, real-world agent deployments. If we're going to have agents doing heavy-duty research, we need confidence in their outputs. My concern here is the computational overhead of all this verification. Does adding local and global checks significantly slow down the agent's operation, or are these checks designed to be efficient enough for practical use?
That's always the trade-off, isn't it? The paper doesn't explicitly detail the computational cost of the verification layers, but the fact that they've released MiroThinker 1.7 and 1.7 Mini as open-source models, offering competitive research agent capabilities with improved efficiency, suggests they've put effort into optimizing these processes. It's likely an intelligently designed system where verification isn't brute force recomputation, but rather targeted checks based on confidence scores or deviation detection, similar to the efficient reasoning with balanced thinking paper's use of confidence.
That brings us to Tinted Frames, Question Framing Blind's Vision Language Models. This is another crucial evaluation paper, highlighting how seemingly minor linguistic changes can completely trip up VLMs.
This paper is a stark reminder that even our most advanced MLLMs are still susceptible to subtle human biases in interaction. Tinted Frames reveals that VLMs exhibit what they call selective blindness. Their visual attention, and consequently their performance, significantly modulates based on how a question is framed. For example, open-ended versus yes-no versus multiple choice. This happens even when the underlying visual reasoning required is identical.
That's quite counterintuitive. You'd think if a VLM can answer an open-ended question about an image, it should easily handle a yes-no or multiple choice version. So, what's causing this selective blindness?
The core finding is that constrained framings like multiple choice or yes-no induce substantially lower attention to image context. They reduce the VLM's focus on task-relevant regions and, strangely, shift attention towards uninformative tokens. This misallocation of attention is the principal cause of degraded accuracy and, crucially, cross-framing inconsistency. Models that answer open-ended questions correctly often fail their constrained counterparts, especially on tasks requiring object grounding.
So it's not that the model can't see, it's that it decides not to see due to the framing. That's a powerful reframing of the problem itself. How do they propose to fix this?
They introduce a lightweight prompt tuning method. It uses learnable tokens that encourage robust, visually grounded attention patterns. The key here is that it doesn't modify the model weights. It's a prompt-level intervention that consistently improves performance across multiple models and benchmarks by realigning the visual attention of constrained framings to match what we see in open-ended settings.
That's an elegant solution if it holds up across diverse tasks. It's essentially teaching the model to ignore the superficial linguistic framing and prioritize the visual evidence. What kind of performance gains are we seeing with this mitigation?
The paper demonstrates consistent improvements. While specific percentage points vary by model and benchmark, the critical finding is the reduction in cross-framing inconsistency. The mitigation strategy successfully helps models re-engage with the visual information under constrained prompts, bringing their performance closer to their open-ended capabilities. It's about making the models more reliable and less sensitive to how a human phrases a query, which is vital for broader adoption.
Okay, one more quick one because it's so fundamental to agentic progress. AndroMem, from interaction trajectories to anchored memory in long horizon GUI agents. This is all about how agents retain information over long sequences of actions, right?
Exactly. This paper introduces AndroMem Bench, a new benchmark specifically for long horizon Android GUI agents. It comprises over 1,000 tasks with an average of 32.1 interaction steps and up to 65 steps, all designed with strong causal dependencies. This isn't just a list of tasks, it's a rigorous test for memory. Their diagnostic evaluation revealed that performance degradation in GUI agents over longer sequences is primarily due to within-task memory failures, not just local action mistakes.
So, agents are forgetting what they just did or where they were in the workflow.
Precisely. To address this, they propose anchored state memory, or ASM. Instead of full sequence replay or simple summaries, ASM represents interaction sequences as a compact set of causally linked intermediate state anchors. This enables sub-goal targeted retrieval and attribution-aware decision-making. Imagine an agent performing a complex sequence like booking a multi-leg flight. ASM helps it remember the anchor points of each leg, rather than trying to recall every single button press.
That makes sense. It's about semantic compression of memory. And the impact?
ASM consistently outperforms full sequence replay and summary-based baselines across 12 evaluated GUI agents. It improves the task complete rate by a significant 5% to 30.16% and the anchored memory score by 4.93% to 24.66%. This is a crucial step towards making GUI agents truly reliable for long, intricate tasks. Current benchmarks often gloss over these deep memory failures, which AndroMem Bench and ASM bring directly into focus.
That's a huge deal for real-world automation, where tasks aren't short, isolated events. The memory bottleneck is a critical one for robust agency.
It absolutely is, and it connects directly to the broader agentic AI trend we discussed. Reliable memory and consistent understanding are foundational for complex, evolving agents.
So looking ahead, what should we be watching for next week, Onyx?
I'd say the convergence of logogram and algogram is hinting at a stronger focus on interpretable AI planning. We're seeing more tools for understanding why agents make decisions, not just what they decide. And keep an eye on new architectures combining LLMs with dynamic routing mechanisms like the hybrid reasoning model as the field continues to seek efficiency and adaptability in specialized reasoning tasks. The emphasis on robust evaluation for agentic systems and MLLMs won't be slowing down either.
Interpretable planning and robust evaluation. That sounds like a solid foundation for the next wave of agentic systems. Thanks, Onyx.
My pleasure, Nova.
And that's all the time we have for this week's AI Research Weekly. Join us next time as we continue to break down the latest in artificial intelligence.
Until then, keep digging into those preprints.